Right. So do I go or?
You are on.
Okay, I'm on. All right. Hey, thanks for having me. People have been asking me if I feel retired, and the answer is I'm never going to feel retired. And that's because I was on sabbatical when I started my retirement, and it's just been like an infinite sabbatical. This is actually one of the first things I've been able to do as a retired person, and that I'm able to come out here and visit family, and it's not Easter, Christmas, or spring break. Okay, it's really cool. I could just come out here and just have a good time. And I've wanted to come to one of these live meetings for so long. This is just great. You'll see more of me in the future. Okay. I'm going to be talking about backyard radio astronomy. This is a subject that has come up over the last few years. 5 years ago, you would not have even considered doing this. But what has happened is that there's been a technology change, and the technology has driven this. And so it's become possible, as you'll see, for someone like me or you to do this. All right. I love it because it's the ultimate DX, in that the radio waves you're detecting are coming from thousands of trillions of miles away. All right. I'm also going to be involved in moonbound. So I'm working on a moonbound project, and there you're transmitting and receiving a signal over 500,000 miles. Well, okay, that's enough of a challenge too. But here you're receiving signals that are coming from light years, thousands of millions of miles away. The signal levels are so low, you're going to see it. It's just impossible. You can't believe it. I can't even believe. I still can't believe I can do this stuff. Is what it comes down to. All right. Now, the difference between radio astronomy and optical astronomy is one of wavelength, or equivalently frequency. In the right here, I've got the entire electromagnetic spectrum, and at the top you've got gamma rays and X-rays, and then ultraviolet, and then there's this little teeny portion here called the visible part of the spectrum. And the wavelengths here go from about 400 billionths of a meter to 700 billionths of a meter, which, compared to some of the astronomy that's been being done now, that's actually long. But to us, of course, it's ridiculously short. We work in centimeters, meters, right? Okay, UHF is in centimeters and HF is in meters. So we're used to radio waves like this. Light waves are, you could fit 2,000 wavelengths of green light in a single millimeter on a ruler. Okay, it's incredibly small. Okay, then as you go down in frequency and longer in wavelength, you eventually make it down to here, where you've got radio and TV and so on and so forth. Microwaves here at 10 centimeters, and then radio, TV up to about 10 meters, then the 100 meters, several hundred meters, 300 meters is the AM band, right? The AM band, 1 megahertz, and so forth. What I'm going to be talking about is radiation that's at 21 centimeters. So it's about that place right there. Okay, it's just inside what we call the radio window. Now, as you all know, as hams, this is what it's great, because when I talk about radio astronomy, if I'm talking to an astronomy group, they don't know anything about the technical nature of it. They don't know anything about it. And I can't talk radio. With you folks, I can. Okay. You know that antenna size is tied in to the wavelength. So an 80-meter antenna, a dipole is 40 meters long, and 10 meters, it's 5 meters long. And you get up to the 2-meter band, it's 1 meter long. The antenna size is related to the wavelength. So when you get up to light wavelengths, the antennas are very different. An antenna for light wavelengths is a mirror. Okay, that's a mirror. Okay, you take a paraboloid antenna and turn it into a mirror, and that a telescope, a regular telescope, is the antenna for radio waves. All right. Well, we're down here in the 21 centimeter range. Okay, and that greatly affects the design of the telescope, and it also greatly affects what you can see or observe. Okay, what you can detect with the radio telescope is totally different from what you can detect with an optical telescope. And the same thing goes for infrared, which is the Webb telescope. You've all seen that. And there are gamma ray telescopes, and there are X-ray telescopes and so forth. They all detect different things, okay? And that's why you use them. That's why you change the wavelength that you go through. This is the opening slide I had, and this is a graph of the opacity of the atmosphere. Opacity is the opposite of transparency. 100% opaque means nothing goes through. This table is 100% opaque. The windows are 0% opaque. They're transparent. The air is not transparent for many, many wavelengths. It's transparent, fortunately, right over here, you can see where the visible spectrum is. It's transparent for the visible spectrum, and it's completely opaque for gamma rays and X-rays and ultraviolet, and it's pretty transparent for visible light. And you know, that's really, really lucky, because most of the energy that comes out of the sun is at those wavelengths. The sun radiates very, very strongly at visible wavelengths because it's at 5,000 Kelvin. If the atmosphere were opaque at those frequencies, it would be dark here all the time. We wouldn't be here. There'd be no light. So I think I don't know if it's dumb luck or whatever that the atmosphere turns out to be transparent there. When they look for life-capable planets in the exoplanet search, they're looking for planets that where the light from the star can get through to the surface, okay? And then as you go down in frequency and longer in wavelength, it gets very irregular, and then you have this huge area here, which includes infrared, where nothing gets through. And that is why they put the Webb Space Telescope out there. This is the area where the Webb Space Telescope operates. And unfortunately, these frequencies are also given off by anything that's above absolute zero. So you have to keep the thing away from local sources of that. So they put it 1 million miles out. And I don't have to tell you about the design problems of putting the thing out there and maintaining it. You know, you've all read about Webb. It's what a piece of technology. Just amazing. But then you get down here, and when you get down to wavelengths about 1 centimeter, there is this huge window where the atmosphere is completely transparent. And it goes from about a couple of centimeters all the way down to about 20 meters, which is, of course, where we operate. And by the way, this is two-way. This is why your signals bounce back in the AHF bands and you have skip, because they won't go through the atmosphere. They bounce off of it and come back down. Well, the same thing happens if it's coming from space. It bounces off and it won't come through. All right, so you can't build a radio telescope below about 20 meters. All right, and if you try and build one shorter than 1 centimeter, it is possible, but it becomes very difficult. Okay, and so you have to either operate here in the radio window or in the optical window, or then you just go to outer space. All right, you go to outer space. So, which is difficult. Okay. The wavelength we're going to use is 1,420.4 megahertz. Actually, it goes out to 13 significant figures. It's one of the most accurate things there is. The Naval Observatory uses a hydrogen maser as one of their frequency standards, coupled to 50 atomic clocks. And that's part of the UTC system out there. It's so accurate, okay? The wavelength here is 21 centimeters, so like that. And a half-wave dipole for 20 centimeters is 10 centimeters. Has anybody here done any work in the 1296 ham band? Probably not. There are people that do that. It's one of the ham bands out there. It's one of those UHF bands out there. It's pretty near this, okay? And if you're like me, I see a acquisitive face out there. You're saying, where the hell did you get this frequency from? What do you mean 1420.4? What is it about that? Okay, well, this is what is known as the hyperfine or H1 or 21 centimeter line of hydrogen. And it's very important in radio astronomy, in cosmology, and in the search for extraterrestrial intelligence. It is such a fundamental frequency, as you can see where it comes from. I'm explaining that people who are doing the search for extraterrestrial intelligence think that this is a frequency that other civilizations would use to communicate. Actually, they wouldn't use this frequency. They would use pi times this frequency to communicate. Because if the signals that I'm picking up come from the hydrogen clouds, I'll talk about this. If you try and transmit on this frequency, it's going to get covered up by that. So they figure, well, broadcast on pi times it. And if we pick up something on pi times this, that's not accidental. It's coming from somebody that is aware of pi and the hydrogen line and so forth. But it's a very, very fundamental frequency, okay? And it comes from hydrogen. The universe is something like 80% hydrogen. The stars are mostly hydrogen. Here on Earth, no, it's not 80% hydrogen here. But the Earth is just this little teensy grain of sand, even in the solar system. The sun is mostly hydrogen, and there's hydrogen all the way out there. And this comes from a property of the element hydrogen, okay? Since it's going to be coming from hydrogen, if you can pick up this signal and analyze it, and I'm going to show you how it's done. It's amazing that a little guy like me can actually do this now. It just blows me away that you can actually map out where this hydrogen is sitting out in the galaxy. And you can also tell if it's moving and measure its speed. That blows me even away more. Okay, that I can accurately do it. Okay, I can accurately do it. Okay, so where does it come from? So who can tell me what is hydrogen? Can somebody tell me the atomic structure of hydrogen? It's the simplest element. How many protons it got? One proton, and therefore one electron. And the proton's plus, the electron is minus, and so they're attracted to each other, and so the electron orbits the proton. Yeah, I see over here. Okay, Bruce. You want me to give you electron quantum mechanics, but it's good enough. It's good enough. It's good enough to a first approximation that's completely accurate. That is completely accurate. Okay. Now, so the electrical attraction holds that electron in there, but it turns out that's not the only force acting on the electron, and I bet you didn't know that, because they found out in the 20s and 30s of the last century. I have to start saying that now, the last century, okay, that they discovered that hydrogen, that the proton and electron have magnetic properties, intrinsic magnetic properties. They behave like small magnetic dipoles. They behave like small bar magnets. And therefore, there's a magnetic force between the proton and the electron. Now, anybody here that's played with magnets, and does anybody here that hasn't played with a magnet, your homework is to get a couple and play with them. But every hand that I know of is at some time in their life play with magnets. If you take two bar magnets and you put them in the same direction, they repel each other. North repels north, south repels south. Flip one of them around and they attract. So when you have the electron here orbiting the proton, if the two magnetic moments are in the opposite directions, there's a slight attraction. And if they are in opposite directions, there's a slight repulsion. Now, this force is like 100,000 or more less than the electrical force. It's extremely small. Nonetheless, it's responsible for what we're going to observe, because this means that there are two energy levels. The energy is lower when they're anti-aligned, and it's a little bit higher when they're aligned. The energy difference here is so small that all the atom has to do is bump into another one and it can put it up in the higher state. Furthermore, quantum mechanics, which I have to invoke at this point, requires that the angle between these two magnets can be only one of two values. They can be either with each other or against each other. No angles in between. Okay, no angles in between. I can't explain it to you. I could prove it to you if I had a couple hours with quantum mechanics, but it's one or the other. When they're opposite, the energy's lower, and that's where nature wants it to be. So you leave it alone long enough, and it'll go down to that state. But if it bumps into another hydrogen atom or a cosmic ray hits it, there's a bunch of other things out there in it. We're talking about interstellar space. It gets bumped up into the higher state. And it's not in a particular hurry to come down. It only takes, on the average, 10 million years. 10 million years on the average before it comes back down. It's incredibly long. That has implications. That number is actually important. So at this point, you should be squinting and saying, well, if it gets into the higher state, it's never going to come back down for the next 10 million years. How can any of them make the transition? Very low probability. About the same probability people will bet on the lottery, okay? But in 1 gram of hydrogen, there are 600 million atoms of hydrogen. And now we're talking out in the galaxy, we're talking about light years by light years by light years of hydrogen. There's more than enough for enough of them to be making this spin flip transition and giving off. What happens is when it's in the higher state and it finally decides to make the transition, it flips over and it gives off a photon, a little bit of radio energy at 1,420.40575178 megahertz with a wavelength of 21.10611405460 centimeters. The longer it stays in that excited state, the more accurate is the frequency that it gives off. This is why the people at the Naval Observatory use a hydrogen maser, which uses this transition as part of a clock. It's so doggone accurate. All right. They figured this out in the 20s and 30s, and they predicted in the 40s that the hydrogen out there in interstellar space would be giving off radio waves at this frequency. And we should be able to pick it up. And they did in the 1950s. After the war, they did pick it up in the 1950s. Except they found one thing, that they didn't pick it up at precisely this frequency. Does anybody know why you might pick it up at some slightly different frequency rather than this 13 or 14 decimal place figure? Yes.
Dielectric.
It's not the atmosphere. I heard someone say it. How do they? Yes, Doppler effect. The Doppler effect. This is precisely how the police catch you. They send out a microwave, it bounces back, they measure the frequency shift. When a siren goes by, it's higher pitched and then it's lower pitch as it goes by. The same thing happens with radio waves. Do we have any satellite operators here? If you have any satellite operators, it's higher in frequency when it's coming towards you. It's lower frequency when it goes away. This is the same thing, except the Doppler shift is a little bit bigger here. Okay, because these things, what it means is when you detect this hydrogen, it's moving. And it can be moving towards us or away from us. And of course, what else could be happening? It's the relative velocity. The Earth is moving people at 67,000 miles an hour. So this velocity that we detect could be us. It could very well be us moving towards it or away from us, okay? So what this does is if you detect this radio wave and you detect its frequency by measuring how much of it there is and its frequency, you can determine how the hydrogen is distributed in the galaxy. And in the 1950s, this is how they figured out that the Milky Way was a barred 3-spiral galaxy. And they're still doing work on this frequency. What's amazing is this telescope I'm going to show you can make these measurements. It's not just a toy. It doesn't just hiss at you. It gives you quantitative results, okay? Now, when I say radio telescope, has anybody here been to Green Bank? I want to go, Anthony. I want to go. If you and Linda want to come down and we can go down there. I'm just outside of the radio quiet zone. I'm almost in the radio quiet zone, which helps me, I think, in this work. But when you say radio telescope, this is what people think of. They think of the very large array, which is 27 telescopes. They think of the Green Bank telescopes and so on and so forth. Certainly, when you look at these things, they're extremely large, billions of dollars now, probably. Yeah, billions of dollars, probably. They require an entire building for the electronics and all the, this is major, okay? And it would seem to exclude anybody like me. Okay, I am aware of how big the universe is, and that makes me aware of how little I am in it, okay? But I can think and the universe can. There's a big difference there, okay? Well, the times are changing, okay? What has happened in the last 10 years or so is among other things, this. I have a big hate-love relationship with these things. I think they have many negative properties, but whether you'll go into that or not, they're there. And so they continually develop electronics and the wireless networks that make these things easier to use in more different places. And what happens is that filters down to you and to me. This happened in World War II. This happened in World War II. All of this fabulous stuff was available after World War II. All this surplus stuff, all this wonderful technology was available to us and so on and so forth. Well, now, transistors that are so quiet, they have almost no noise, have now become affordable and so on and so forth. Computers, my God, the computers we have now are so powerful compared to even the Atlas and the IBM 6070 and the Maniac computers, that the computing power, I think this thing grossly surpasses all of those. Okay, and the computing power in a laptop is unbelievable. Okay, the result is that it is now possible for an amateur to build and operate a personal radio telescope. Now, this is challenging for an astronomer because of the technical aspects, but for hams, it's less challenging because you understand a lot of the technical aspects of it. Okay, there's what it looks like. There it is over there, but I don't think that's on camera. It's over there. Okay, it's a 1 meter Wi-Fi dish. This one's for 2.4 gigahertz, but you can use it on other frequencies, obviously. It's a 1 meter parabolic reflector. It's on a little tripod. You need some special electronics to go with it, and then you need software. But all of this stuff is affordable, as you're going to see, and within the range of just about anybody. It's this that you have to be able to know what's going on. Okay, and that's why I'm here. Okay, the gain of these antennas, this at 2.4 gigahertz, this thing has a gain of 24 dBi. What's the gain of a big tri-bander? 6 decibel. I mean, this is take the equivalent of 4 tri-banders and no, let's see, 6 decibels. Oh my gosh, you'd have to have doubling gives you 3. It's unbelievable gain. And the beam width is only about 12 degrees. Now that's optimistic because we're using it on a lower frequency. So it's probably maybe 20 degrees or so, and the gain's less, but it's enough. And you can buy it on Amazon. I have a nice one, powder coated, waterproof, cast aluminum, so it doesn't bend, it holds its shape and so on and so forth. Okay. The key thing here is that a radio telescope is a system. Most people point to the telescope at Green Bank and say, oh, there's a radio telescope. Well, that's like pointing to a tower you have and saying, there's a radio station. No, that's the antenna. The station's down here. They got studios and they got the transmitter and the receiver and the whole thing. This is a system. Your ham station is a system, and so is a radio telescope. And it's been revolutionized by the advent of the electronics and by computers. Computing has just done amazing things. Okay. This is, of course, the antenna. Most antennas are parabolic at these frequencies. I'll talk about it. A parabola is special in that when a plane wave comes in and hits the surface of a parabola, the parabola is a reflector. That's all it is. It's just a reflector. Reflects the radio wave according to the law of reflection in physics. And the shape of the parabola is such that any wave that strikes it coming in parallel is automatically brought to a common point called the focus, which is the feed point. And there's something else which most people don't even think about. It also turns about that radio wave that's reflected travels the same distance. If it comes out here, it comes in more directly. If it comes down here, the total path to that focal point is the same regardless of where the radio wave hits the reflector. Okay, and this is independent of frequency. The trouble with these parabolic reflectors is they have to be about 4 or 5 wavelengths in diameter to be effective. Below that, your Yagis, and you can do radio astronomy with Yagi if you want. You can build a bunch of Yagis for this frequency, and some people have done that. But heck, this works too. Okay, but you have to go into a low noise amplifier, and this one also has a bandpass filter. All right, this frequency is so special that nobody is allowed to use it commercially. It's forbidden. There's a guard band of frequencies on either side that nobody is allowed to use. But that doesn't mean all that wonderful stuff out there like these and other things can generate harmonics and noise and all other kinds of spiky crap, as I call it, can't produce stuff that could get in to that low noise amplifier and get through. So in this case, since you're interested in one frequency, it has a built-in filter that cuts out anything that's too far away. Okay. All right. Then you go into a receiver, and the receiver tunes in the signal and filters a little bit and so on and so forth. I'm sure some of you have who have software defined radios. Anybody have flexes and stuff? All right, a flex is like this. Okay, though the bandwidth here is a little bit bigger. This thing has a bandwidth of 2.4 megahertz. It takes half of the 10-meter band into it at the same time. Okay, and then what's different nowadays is it's digitized and sampled, and then it's fed down a USB cable where the computer processes it. And we don't listen to these. These are unmodulated signals. They're unmodulated, but they do produce a spectrum display. So you take your spectrum display on your transceiver and freeze it, and it produces a frozen spectrum, which is what we're interested in. And we want to either be able to graph that and look at it on the computer, or print it out, or store it in a data file. That's very important. If you want to actually do something with it, I mean, after you get over the holy cow, I'm actually picking it up, this is fabulous and stuff, then you go, what do I do with it? Well, that's when you get to working with the data. Okay, I can't believe the first time I ever saw the signal, I said, I can't believe this. You know, and it was actually a detailed signal. When I first got it up, I just couldn't believe it. Okay. So the first step in a whole system is what's called a low noise amplifier. We got some UHF, VHF guys out here, gals out there. Okay, what do you go up to there, Frank?
Just 440, not that much.
Oh, 440. Okay, I'm in the process of building a 432 converter.
Okay.
Okay, it's got a 0.8 dB noise figure. Okay, the thing is called a sawbird. The bird comes from the geeky people that design it and market it. Okay, it means it flies, right? But the saw, does anybody know what saw means? Surface acoustic wave. Okay, inside this thing, just to give you some of the specs, it has 40 decibels a gain, and it has an amazing 0.8 decibel noise figure. This is without cryogenic cooling. Now the research telescopes take the whole thing. They would take this and immerse it in liquid helium, because you get into the point where the very wires, the very metal of the telescope, the very wires, the very buildings around you are radiating energy at this frequency, because they're not at absolute zero. Heat produces this random vibration. That random vibration can be picked up and generates noise that can affect the signal here. All right, you got to deal with that. That's why when you go down to Greenbank, they got a block this big through the north or the whole corner of West Virginia, where they have cops out there, their cops that go out and find anybody causing RFI. All right. So you got to deal with that. One way to dealing with it with the big boys is you take the amplifier and you put it in really, really cold liquid helium where it's almost at absolute zero. I don't have to tell you the problems involved with that. Okay. Though it has occurred to me that I could consider, I have the connections where I could conceivably at least use liquid nitrogen. Okay. But little steps. Okay. The 0.8 of a decibel noise figure means that when the signal comes out, the amplifier has only added less than 1 decibel of noise to the whole thing. Now, this is not true if you've got a telescope out in space, but for terrestrial telescopes, it means that the amount of noise added by the electronics is essentially inaudible. Now, if this were a Webb telescope, that it turns out it works differently. Okay. The transistors they use in here have been developed for cell phones and all these remote things. They're expensive. They're like $7 for one transistor. Really, that's not expensive. It is when you think a transistor like a 2N22 is 10 cents. Well, 22, they're more expensive, but the common transistors are a dime. So these are expensive, but they do the job. Okay. And it does have this filter, which is 63, it's 65 megahertz wide. So 30 megahertz on either side, it doesn't affect the signal. And then outside of that, it rapidly cuts it out. You don't want any kind of interference coming in, getting amplified, overloading it, and then generating all kinds of garbage, which you can see, by the way. I see a lot of this garbage, okay? It looks big, but there it is, folks. That's it. How much do you think it costs? Less than $50. $45. That's it. I mean, that's throwaway change nowadays. That's throwaway change, $45. It's powered through the feed line. It gets its power from the feed line. 5 volts comes in on the feed line. It's called a bias T. It's powered along the feed line. Okay. So it goes into this, and this mounts right on the antenna. The antenna's got 3 feet of feed line. That's it. 3 feet of coax, and then you go into this. You have to get this at the antenna. And you go down to Greenbank, they have the low noise amplifier right at the antenna, okay? Inside, that's what it looks like. They've got an amplifier, the bandpass filter, they have 2 of them, and then it comes out. There's no gain control, it runs wide open. Full tilt boogie all the time. You need so much gain to try and catch this signal, it's ridiculous, okay? Then it goes into a receiver. This blows me away. The receiver is based on 2 chips, this one here and here. This is a processing chip, this is the tuning chip. These things were made for digital broadcast television when we switched over to digital TV. They were designed to plug into a USB port. You hooked an antenna to it. You could get broadcast television, digital high definition TV on your computer. But the geeks got a hold of it, started playing around with it, redesigning them, and they improved them. They laid it out better so that it will work on broad frequencies. It corrects directly. Here it is. There it is. That's it. Okay. This is a software-defined receiver that goes from 500 kilohertz to 1,766 megahertz with a resolution of 1 hertz and a temperature stability of 1 part per million. 1 part per million, which is really, really good. Okay. Price, $29.95. It's insane. That's absolutely insane. You know, I mean, if it were the old days, I'd be afraid about carrying it around, but you know, it's $30. This one has got special things in it so that it heat sinks it properly. Some of them won't, some of the cheap, this one is so good, they're actually forgeries. They're counterfeits. So you got to be careful. Go to this website and buy it from them. Plugs into the USB port. It hooks up directly to the the preamp so that there's no feed line between them. These are called SMA connectors. It hooks up like that. And this hooks right onto the antenna. And this runs through a 30-foot USB cable to the computer. Okay, that's it. All right, that's it. What happens though, this blows me away again, is that somewhere in this thing, they have a super heterodyne receiver. It gets it down to about 28 megahertz, and then they digitize it. Okay, what that means is somewhere in here, there's an analog signal, that you could hook into your radio at 28.5 megahertz. But they have a digital to analog converter that will sample it 2.4 million times a second. When I do audio, professional audio, it digitizes the audio signal 44,000 times a second. This is 2.4 million times a second. And so what ultimately comes out of the receiver and the preamp into the USB cable, and you got to use USB 3 cable, because these things draw a fair amount of current. This is too thin. This is okay if I just want to play it in the room, but I have much thicker cable for the 32-foot run. What's coming down this is 2.4 million numbers per second into the computer that represent that signal. That's what's coming in, okay? You go down to Green Bank, they're doing the same thing, except they do it a little bit faster, and the computer's the size of this room. So the computing is just as important as the antenna and all the other analog stuff. It's just unbelievable, okay? By the way, I'm taking this down to Green Bank. I'm gonna talk to them down there. I want to operate it on their lot because I want to see what the background noise is. But I got to get their permission, and I'm sure I can do that. Okay, I can wangle that. The software, you should all be interested in this, because if you just get a hold of one of these babies for $29.95 from rtlsdr.com, and you go to a place called airspy.com. It's called SDR Sharp. It's European. They don't call that the pound sign. That's the sharp sign in music. So it's called SDR Sharp. I'll tell you a little story here. When I first was getting into this, I told my wife, I said, I've entered a different world. She says, what do you mean? I says, well, I've got to buy the Sawbird Pro Plus 3, then I got to get the RTL SDR receiver. Then I got to run an SDR Sharp and use the FD login, blah, blah, blah. She says, what the hell are you talking about? Okay. A lot of this came from geeks who got into this. No disrespect to them, because they developed, this is a beautiful piece of software. You get this, and you get this, and you got yourself a receiver that'll go from 500 kilohertz up to 1766 megahertz, AM, FM narrow, single sideband, blah, 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 and any other mode you possibly want, because the software can take plugins. You can get ghosts, satellite decoding software, so you can get the direct pictures from the ghost. You buy a different preamp for the ghost frequencies, the geostationary satellites. You can do that. But it's incredibly powerful. It's well documented. The last big book of instructions is 186 pages. Now it's over 200 pages. And it'll do just about anything. Okay, just about anything. You just download it, and it'll run even on Windows 10 and before that too. I think it'll run on XP as well. So these people really did a good job. Okay. What are we interested in the end? Well, how many people have seen this kind of thing? Any of you have got your flex receivers that got this, okay? What we're interested in is this part up here. You do realize that the waterfall display is exactly the same thing as the RF spectrum. It's just a different way of showing it. However, when you get the waterfall display set just right, you can sometimes see stuff there that doesn't show up in the spectrum. So they're both useful. But what we're really interested in is this part up here. We want a graph. It's a graph of each frequency that's present and the amplitude of each frequency that's present. That is what we want, the RF spectrum. What frequencies are there and how strong is each one? That's what we want to know. If it wasn't Doppler shifted, it would be pretty boring. Can anybody tell me if the signal weren't Doppler shifted at all, what would the, yeah, Anthony, it would go boom, and that's it. That's it. It sure the hell doesn't do that. It definitely does not do that, okay? Once you learn how to get everything running, this is a typical output from the computer. Once it's settled down and it start collecting data and so forth. And over on the left here, this is what the averaging software puts out. And you can see if you read down here, this is 1419 to 1421. It's about 2 megahertz wide. That spike is called a spur. We hate spurs. That's interference. That's actually generated internally, but there is what the signal looks like. Okay. And what's great is that there is a plug-in program that you can get that goes with the SDR Sharp. There's a plug-in program, an auxiliary program, which will do this that we see here, and you can freeze the spectrum. You'd love this. I don't think you can do this on any of these flex radios. If I could freeze that spectrum and then spit out the numbers, the exact frequency numbers in a text file, so I could manipulate it as a scientist, I'd love to have that. This lets you do that. It gives you a text file, one column's the amplitude, the other column's the frequency, and then you can graph it and analyze it. Okay, that's important. On the right is an example of what I got when I first got the system working. After some fits and starts, the vertical line that you see there is at 1420.4 megahertz. And then you can see that there's a whole bunch of spectrum out here that is higher in frequency. So Anthony, what direction is the cloud going if it's higher in frequency? It's coming towards us, or we're going towards it. The Earth is moving at 67,000 miles per hour, folks, which you're going to see is something amazing. I'm going to show you at the end here. Okay. This was done over several hours. When I first got it going, and here's one of the beautiful things. If you look at the times here, 3 p.m., 4:10, 5:42, 4:42. This is in the afternoon. This is in the daytime. You can do radio astronomy in the daytime. You don't have to wait for the night. Okay. The night might be beneficial, but you don't have to. You do it in the daytime. Okay. And I first got this thing going. And once you get it running, it will do an integration. I'll explain this computing process, which is utterly amazing. But it'll obtain a piece of data, and then it will write that to a file, a text file, frequency and amplitude. And then you say, okay, every 10 minutes, make an observation and spit it out. Because what's happening here is, I'm going to talk about this, the telescope is not moving. The Earth is turning. So the telescope points at one part of the sky and the sky moves past it. Okay. I decide what I'm going to look at by the time of day that I'm going to go and set the thing up. That's how I'll talk about this. Okay. So what I did at this first light was I just set it up, pointed it straight up. I'll explain this, and let the sky go by. And every 10 minutes it wrote out a data file. And we went to dinner and I came back and I got all this. What you'll notice here, most importantly, is if you look at the blue plots shifted probably because a cloud came by or something. I'm not sure what caused that, but the basic shapes, notice first of all that the shape changes. The bottom graphs are almost straight, but you see the two humps here? You see there's a, right around here on the red, it goes like this, and then like this, and like this. That means there's 3 hydrogen clouds that I'm detecting here. And by looking at where that hump maximizes, I can measure the frequency or the velocity of that hydrogen cloud with remarkable accuracy. Okay. Well, if you do one run and spit it out, that's what you get, folks. Okay. That's what you get. Now, on most of your ham software, well, I guess in SDR, you can have it set so that it updates very rapid. And then it just does this. You could have a spectrum like that, but if you do it again, you get a different spectrum. What you have here are random frequencies and random amplitudes. No apparent signal, random frequencies, random amplitudes. This is called noise. This is called noise. It would appear that there's nothing there. There's nothing there, okay? Do it a dozen times, you get the same thing, okay? The fact that it changes means it's not an actual spectrum. If you did this 10 times and you always got exactly the same thing, spike for spike, that's a spectrum. This is not, this is noise, okay? What you have to do here is you have to use what is called digital signal processing. And I'm going to show you how this is done because I've been able to come up with a physical system that shows how this happens, okay? What you have to do is increase the exposure. You know, you expose longer, you get a better signal, okay? This isn't something you usually do in radio work, okay? Unfortunately, just listening longer doesn't bring the signal out. But bear with me because I'm going to show you how this works, all right? Suppose rather than display it on the computer, we display it on an artistic display. I take this wall over here and I hang one, let's suppose instead, if I go back, is it page up, Anthony? If I want to display this in artistic fashion, first of all, there are 1,024 different frequencies there, and the strength of each one is being shown. And it's all over the board, right? It's everywhere, okay? Let's drop that down to maybe 100, just 100, okay? Just 100 different frequencies. And to make an artistic display, I take 100 glass tubes that are the size of a penny, and I string them up against the wall, nicely next to each other. And let's also suppose that we have a pure signal, Anthony, and it's only got a signal amplitude of 2 out of maybe 100, okay? 2. And also the ridiculous situation that we have no noise. Dream on, okay, but we have no noise. Well, that means of all those tubes, I take 2 pennies into the one corresponding to that frequency, and I plump them into that tube, and I leave everything else blank. Would you be able to see where the signal was then in that case? If there's only 2 pennies in one tube and nothing anywhere else? Yeah. Yeah. Oh, there it is. There's 2 pennies in that tube right there. There it is. Yeah. Yeah. Okay. But we do have noise. So now I take about 100 pennies and I randomly distribute them through all of the tubes, including possibly the one that has the signal in it. I take 100 pennies and throw them in at random. This is important. It's at random. Some might get 3 pennies, some might get 2, some might get none, some might get 1. It's chaos, but noise. Now, can you find the signal? Absolutely not. No. No, can't find it. This is the case here. That's the case here. Somewhere in this barrage, there might be a signal. But you know, what if I threw in 800 pennies instead of 100? This is even worse than that, as you're going to see. But let's go back to our case. Now, what if I left those pennies that I just threw in the noise in the tubes? And I took another sample. I take 2 pennies and I put them into the signal tube, I'll call it. And then I take about another 100 pennies and randomly distribute them through all of the tubes. Are you going to be able to see the signal then? I don't know. Okay, what if I did it 100 times? Now, suppose there was no signal and I did it 100 times. What would I have after I took empty tubes and randomly distributed 100 pennies, roughly 100 times? What would I have in the end? A strip line, but is it perfectly flat? No, I'm gonna have on average 100 pennies. Some are gonna be more, some are gonna be less, but on the average, it's gonna fill up and I'm gonna have about 100 pennies in every tube. Everybody with me? This is a direct analog to the digital signal processing. Now I do it with the signal present. So I put 2 pennies in the signal tube, put in 100 pennies, do this 100 times. Now what do I have? I'm going to have an average 100 in every tube, but how many am I going to have in the signal tube? About 300. It's going to stick out like a sore thumb. And if I now, since I know that I put in about 100 pennies in each tube, I subtract out 100 from every single tube. And if it's less than 100, I just take out all of it. What am I left with? A signal of about 200 and then nothing in the others. And if I divide that by 100, if you want, then I've got very little down here and I've got those 2 pennies visible again, even though when I do a single run, you can't see it. This is called signal averaging. All right. Well, in our case, this is what it does. This program does this. It takes those numbers coming down from the computer, figures out for 1,024 different frequencies, the amplitude of each one. That's a scan, and it stores that. And then it does it again and adds it to the previous ones. And then it does it again and again and again and again, as many times as I tell it to. Okay. Well, this is what it does. You take a background reading, you disconnect it from the antenna, and you put, that's a dummy load, folks. That's a 50 ohm dummy load. And you hook that baby on and you tell it to measure the background. Okay. And then after it's got the background, you go off, hook the antenna on, and you say, go. So now it's doing it with the signal. Okay. This is what you get. You do it 100 times, you got nothing. You do it 1,000 times, you got nothing. You do it 3,000 times, you might barely be able to detect that there's something there. You do it 15 or 16,000 times, which is over here. And now you can start to see that, hey, there's a bump there around 1420.4. You do it 125,000 times. And now you've got a definite bump and you've got structure. That spike is again interference. You do it 1,000,000 times. You tell it to average 1,000,000 scans. And when you do it that long, you finally have a clean, crisp spectrum with a definite shape. Okay. Don't think small. Don't think small. You know how long it takes the computer to do this? Less than 9 minutes. Now, my computer is a very fast laptop. It's got double signal processors in it. It's very fast. This is what they're doing at Green Bank. They're calculating this business of scanning and getting the frequencies and the amplitudes. Anybody heard the term fast Fourier transform? That's what it is. The computer performs a fast Fourier transform in a 2,000th of a second, stores the results, does another one, stores the result, 2,000 times a second. It does this, adding it up, then it subtracts off the background, and this is what you finally have. Okay. Get a bigger antenna, well, then you can maybe do it fewer times. But if you get a bigger antenna, you know what happens? You try and detect something even weaker, and you still wind up doing it. Because we always push our stuff beyond what it's capable of. It takes 1,000,000 scans to do this, okay? Now, how do you point the telescope? Well, Jim was asking me this. He says, well, I don't know if we can see anything there, okay? At the moment, the way I am doing this is where I read about this and so forth. This is called a zenith transit telescope. That's how it looks when it's in the yard. It's straight, just like it says here, straight up at the sky. You point it straight up at the sky. There's no ambiguity where you can use a what do you call it, a plumb bob, but I just eyeball it and bump it around until it's straight up. And you leave it there. And then the sky turns past it. And if you want to look at a particular part of the galaxy, you just wait until that moves into position. Okay, so you point it straight up. How do you know when it's going to be in position? You use planetarium software. There's a beautiful product called Stellarium. This is another European written thing that is shareware. Unbelievable that these people, you know, I need to send them $100 or something just because he did such a great job. It puts on your computer the sky at any time that you want to know what it's at. Okay, here's an output of Stellarium. Okay, you can barely see there the line. You turn on the azimuth and elevation lines, and right here is where they all come to a point. At the time that I took this, you can't see it. This was at 2 p.m. on January 1st. This is where the telescope was pointed. Okay. If I want to look at a different part of the sky, I just go forward and backwards and find out what time is it going to be there. Okay, 4:15. Okay, I'll start my scan at 4:15. Whatever time you want. Okay, it's simplicity itself. Okay, you hook up these two items get hooked up to the antenna, and you run. I have 32 feet of very heavy duty USB cable. These things draw some current. Don't get cheap cable. Don't get cheap. You got to get the good stuff. Okay. I've got 32 feet of cable and it seems to work. This gets hooked up on there where the end connector is at. There's an adapter there. You run the cable into the computer, you run the software, and there you are. All right. All right. The software obviously tunes the receiver. It supplies power to the receiver. The receiver supplies power to the preamp. So the power goes in here. You know, this gets plugged on there. This goes onto the antenna. This goes in. This goes up to the antenna. You can do all kinds of things with it, but essentially you set the frequency to the middle. And what this does is it receives not a single frequency, folks. It receives a 2.5 megahertz wide slug of spectrum. It takes, you know, if I set it to 1420, it goes from 1419 to 1421 point something. It takes all of that and converts it down to 28.5 megahertz, digitizes it and puts it into the computer. And then the computer processes it and tells me how much of each of those frequencies is present. That's what I want to know. Okay. And then you have to do the signal averaging process. Okay. And as I mentioned, this is what it looks like when you do it. When you finally get to 1 million scans, you finally get something like this in the output, which I showed you earlier, or something like this. Okay. And finally, this is almost at the end here. This is a scan that I did on January 1st. You can observe when in the rain or whatever, but I don't like rain and I don't want my equipment to get wet. And I don't think rain getting into a surface acoustic wave filter is going to do any good. So I am lazy and I wait for it to be sunny weather with no clouds. And it was like that on January 1st. And this is one scan that I got. I scanned it over several hours, but I intentionally did it so that I was looking at exactly the same part of the sky that I was looking 1 month earlier. And I don't know why I did that. I just, you know, I figured out, it turns out as the sky rotates, as you go through the year, it over rotates. And so if you pointed it at a certain place at 4 o'clock, you got to, for every month, it's 2 hours earlier. So I did this observation at 2 o'clock in the afternoon on New Year's Day. Okay. And I did 1 million scans here. And I've cut off some of that stuff that was uninteresting. If you go back, page up. Yeah, if you go back, I started here at 1420. I cut all this uninteresting stuff out and just kept this stuff on the right part of the graph, okay? And I got this, okay? And there are coordinates of the galaxy there, and I also changed some things around so that I just arbitrarily called the strongest part of the signal 100. I manipulated the data and said this, the largest amplitude's 100. So these are all percentages of the maximum one, okay? And the vertical line is at 1420.4 right there. And Anthony, that's exactly where the spike would be if there were no Doppler broadening. But obviously, there's a lot of signal right at where it's supposed to be, but there's signal to the left of it and a huge amount of signal to the right of it. Okay, I'm almost done. All right. Now, if you're like me or like the public, I always would tell my students, who cares? So what? Well, to me, to us, like we're scientific, this is, I think this is really cool. But what good is it? Well, if you have the numbers, what you have here, it's a brainless calculation to change from frequency to velocity. So when you pick up those satellites, if you know what the beacon frequency is, you can calculate how fast that satellite's approaching you or leaving you. It's very easy. So I did this for this set of data. Now you notice it flips it over a little bit. But now if you look at the bottom, it's not in frequency, it's the relative velocity in thousands of miles per hour. Thousands of miles per hour. And you can see that on this day, the strongest signal is shifted slightly to the right of 0. It's actually at about the 10,000 mile per hour mark. So that cloud that's producing that bump is on the average moving away from us at about 10,000 miles an hour. Or we're moving away from that. I mean, everybody, it's relative velocity. But then look over on the left, there are two bumps. And this one is peaking at about, 180 or 170,000 miles an hour towards us. So we're approaching the cloud or us, we're approaching each other at about 170,000 miles per hour. And there's evidently another cloud out there, this bump here, which is almost as strong, the signal is almost as strong, that's approaching us at about 100,000 miles per hour. What they did is they did this in the 50s, which much more complicated equipment. And this is how they figured out how the galaxy was structured. I've actually looked at diagrams of the Milky Way galaxy, and I think what you're seeing are the spiral arms. I think you're seeing a couple of the spiral. I looked at where's the Earth, and we're looking this way. Son of a bit, where there's an arm there, and there's an arm there, and there's an arm here, and I think you're seeing the three of those. Okay. But wait, if you order now, I'll include a Ginsu knife. Because I realized that I had subconsciously done this 1 month after I had done the same observation in the same place. So I went back and I extracted the data from this red file or the green file there. You can see the green line there has got the two bumps, which was taken at 4:10 p.m. And I brought that in too and plotted them both. So the upper graph was taken at 4:10 on December 2nd, and the lower graph was taken on January 1st, 2 hours earlier because of the change in the sky. So I'm looking at exactly the same part of the sky, but 1 month apart. What do you see as the difference? Now, I had to change the scale, the upper one, to bring it down so that, they're on the same piece of paper. What is the primary difference between the two graphs? There's an amplitude difference, slight, yeah. But that's not the really important thing. You're almost there, Anthony. Do the peaks coincide? I dropped these lines down from the top one at the peak. The top of the bottom graph is shifted over. And on this one, the peak is again, all of the peaks, if you do it for the middle one too, all of the peaks are shifted over by about 10,000 miles per hour. All three of them are shifted by 10,000 miles an hour. What's going on? They're all shifted by the same amount. That's important. They're all shifted by the same amount. Now, what is the likelihood of all three of these hydrogen clouds all deciding to change speed at the same time? What has happened here? Yes, the Earth is going at 67,000 miles an hour in its orbit, and it has turned slightly towards the direction I'm pointing this thing in its orbit. And so the relative velocity has increased by 10,000 miles an hour. I predict that if I do this over the next year, I'm going to see these bumps do a yearly shift up and down as the Earth moves around the sun in its orbit. And that's only the first thing I've uncovered with this crazy thing. Okay. So this is where I was looking. This is where, right up here, it's hard to see, right there in the constellation Cygnus is where I had the telescope pointed. And so I can wait for another nice day here, figure out using the software in the computer, where is that going to be? What time? Okay, then I'll take my reading then. Then you can start to point it in different parts of the sky. Now, what's really cool here, and I'm surprised no one has picked up on it. This graph, this picture is at 2 p.m. Yeah, 1400. People say, what's this bright star here? That's the sun. The software lets me turn off the glow in the sky produced by the sun. So the sun just shows up as an artificially bright star. You can actually see down here, there's Saturn, Jupiter, and some Jupiters over here. You can see down here. Here's the center of the galaxy. And where I'm actually looking in the galaxy is the galaxy's flat. If this is the center of the galaxy, I'm pointed over here about 78 degrees. I'm pointing like over there. Later on, I'll try pointing here or something. Just what the hell? It's fun. That's it. Any questions? Any questions?
You really going through that again?
No, seriously. I mean, yeah, Anthony. I haven't tried it yet, but I should be able to pick up sun noise. But that's going to be broadband noise. See, Frank, you gave me that picture. Were you the one who gave me the picture of the telescope?
At VLA.
At VLA. Yeah. Well, the way they would have done this in the 50s without computers is you would feed the output of a conventional receiver tuned to 1420.4 megahertz, but you would have a receiver that you could tune up and down. And all you would be getting would be hiss. And you want the hiss. This is the opposite of what we're used to. You want the noise. You want the noise to push an S meter up. So you would tune it to a certain frequency, read the S meter, tune it to the next frequency, read the S meter, and then make a graph. And you would eventually come up with, with something like I had up there. Okay, that's the old way of doing it. Nowadays, you sample it. You digitize it. And you turn it into a stream of numbers. And then there is a special computer algorithm called a fast Fourier transform. Computer people will tell you that probably the most famous of any computer algorithm that came out of the 20th century was in 1965 when these guys came up with this thing called a fast Fourier transform. You take a bunch of these numbers equally spaced, it chops on it, and it tells you these are the exact frequencies present, and this is how strong each of them is. And that's essentially what your DSP is doing in your SDR receivers. It's calculating these simple Fourier transforms and then graphs it for you on your radio. But one of the uses in the 60s, when the supercomputers, you might have heard of the 6070, I think it's called. The 6070 is was the IBM mainframe. If you've seen Hidden Figures, if you folks seen Hidden Figures, that's a 6070. They were, I think my Commodore 64 had with 128K of memory had as much computing power as that thing did. Okay. And nowadays it's got one of the main uses of those first supercomputers. You might have heard of Maniac. And then there was the Atlas. There's the I don't know. One of the primary uses of those supercomputers was calculating the hydrogen bomb equations, calculating the weather, and processing the radio data from the first big radio telescopes. And if you go and look at, there's a multi-antenna array in Chile, Atacama or something, I forget its name. The computing aperture synthesis computer is like this whole room. I mean, just row and row and row and row and row of computers just to put the signal together. Then they do all this other stuff. Computers revolutionized. For this, it takes 1 million computations to get there. But hell, that's 9 minutes. So what? And I haven't started yet. It should be obvious. If I really wanted to get a super great spectrum, I have how do I get back here? Shift F5. Function F5 or Shift F5? Oh, function F5. No. F5. Wait a minute. Where's function 5? Run it again for me so I can.
Just have to show up again.
I have it show up again and I'll cycle through it. Just get it running again. What's the magic keyboard?
Should be a
Wait,
5.
okay, got it. Wait a minute. There it is.
I can't see these keys. These are really tiny.
Okay.
Yeah.
Oh, okay, there we go. Okay. What they do at oh, there it was. Page down. Okay. Let's go down. There we go. There. See what they're doing in the left one is rather than have one huge dish, they take a whole bunch of small dishes. Now there's a trade-off. There's always a trade-off. If you want signal strength, you have to have area. Sheer area. This is true with Yagis and everything. The more antenna area you have, the more signal that you pick up. That is absolutely true. But it also turns out if you start moving the antennas far apart, the directional accuracy becomes better. So if you want to pinpoint a radio source, you need maybe 2 antennas 300 meters apart. Now you could have a single 300-meter telescope, and you know what that was called? That was Arecibo. But if you don't need all of that, Arecibo picks up, 300 meters is quarter mile. I don't know, it's huge, okay? But if you don't need all that signal pickup, you just want to say, where's the darn signal coming from? That's a different story. I haven't done anything about that. Then you have 2 antennas far apart. And if you combine the signals, then you can get very good directional accuracy with that, but you don't pick up nearly as much signal. And so what they do over here at the VLA is they can stretch these things out over miles and effectively have an antenna that's several miles across. It doesn't pick up the same thing as a 1 mile dish. Geez, that would be something, wouldn't it? Okay, but it can pinpoint with very high accuracy. And then has any of you heard of there's another one where they actually take this to the size of the Earth. They actually take a radio telescope in Chile, the VLA, they take one over in Europe, they take another one here. Some of these are almost on opposite sides of the Earth. So the baseline is the diameter of the Earth. And using that array, they were able to see the black hole in the center of our galaxy. And what they have to actually do, it's amazing what they do. They take that data, they have a data stream coming out of the antenna, just like this. That's why they take that data stream, but it's a hell of a lot faster. And they have it tied to an atomic clock. You got to have an atomic clock. Atomic clock won't go off 1 second in 300 million years. They have an atomic clock. They're only $60,000. What the hell? Okay. And they mark every one of those samples with the time that at the time it comes out, and they store that onto a hard drive. So you got this telescope over here streaming out its data, and every little piece of data they have to take into account it's oh my gosh, the cable lengths affect it, the computing time affects it, all of this. They have to work all this out, but it's all run into a hard disk drive, and every single one of those is timestamped. And they do that for all of the telescopes. Okay, all of them. And then they bring it to a supercomputer, bring all those hard drives together and read the data off. And by knowing precisely when they received every little signal, they can synchronize the signals from all of these, 4 or 5 different telescopes. And by doing that, they can get the effect of a single telescope that is the size of the Earth. And with that, they were able to see the black hole, this little blob, you might have seen it, little furry blob at the center of the universe. It's incredible.
Does helium have a similar line or lines?
Okay, this is a great point. All molecules have these lines. And hydrogen, this line is the simplest element. In fact, this frequency is so fundamental that on the plaque, remember, it's 21 point blah, 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 whatever. They actually put on the plaque on the Voyager that went down, they put a diagram similar to this on it, on that plaque. And then they showed the radio wave coming out, and they showed one wavelength. And then they would show a naked man and a naked woman standing there, and they would show how many of these hydrogen wavelengths, so that somebody intercepting that would certainly know about this transition in hydrogen and could tell that a man was, 5 wavelength, they could figure out, they showed the locations of all the things, all in terms of this fundamental frequency. But you might say, how the hell do they know that there's water out there in space? The answer is that water has certain transitions and radio wavelengths, but they're typically up into the microwave region, which is difficult to get through the atmosphere. And what also will happen is you can get an absorption spectrum. If you have a huge source of radio waves, a broad source of radio waves, a very broad source of radio waves, many, many frequencies, and then you put hydrogen in between, the hydrogen will absorb that wavelength, and what you'll get is a dip in the spectrum. Instead of having a peak, you'll get a dip in the spectrum. And you say, oh, there's hydrogen there. Or there's methane, or there's ammonia, or OH, or this is how they've detected many of these molecules out there far out, because they either give off or absorb. Sometimes it's in microwave radio lengths, sometimes it's in optical wavelengths. This is why you want to have telescopes that can operate at all these wavelengths. All these molecules will do this.
The reason I asked that question, there's a star called Betelgeuse that is rapidly finishing up its helium or hydrogen.
Red giant in Orion, and it's beautiful. Teddy, we looked at I don't know, just last week is, wow, Mars, by the way.
I was just wondering if you would be able to see enough change in the hydrogen line or maybe a helium line to show that it's when it might. No.
What you're talking about there, now we're talking about lines. Most of the observation is done at visible wavelengths. Okay, a lot of these things are, hydrogen has visible wavelengths. If you take hydrogen and you stick it in a tube and electrify it, you got to break it up into it's a fundamental, but you'll get red, blue, green, and blue violet at very specific frequencies. These are at optical frequencies. A lot of the telescopes that are optical telescopes, you don't look through it. You run the light through a prism that breaks it up and you get the spectrum of the light. And that is another way of telling that which elements are there. If you take the spectrum from the sun, Fraunhofer did this, and you run it through a spectrograph, it's got to be a hellacious thing, you know. What you'll find is dark lines all through the sun's spectrum. And what's happening is there are elements outside the photosphere of the sun, where it's very hot, that the light from the sun is coming through that, and certain elements are absorbing the light and causing these black lines. And you say, well, hell, there's hydrogen, you know, here, there's neon, there's iron. You can tell how much of the elements are on the sun, and they can do that with distant stars as well. So they can do that with something like Betelgeuse. And when they do it to the extreme, with the really far stars, the optical hydrogen lines, I could name some of the wavelengths, but they look at far off galaxies and find the hydrogen line there, and they find it's shifted down into the red. It's not where it's supposed to be. That's the expansion of the universe, that the further you look back, the more the optical lines, well, any lines, but the optical ones, which are much stronger, are shifted in the red. Why are the optical lines stronger, by the way? Because the sun is a boiling hot star. You know, it's a huge thing. It's red, you know, that's yellow hot. I mean, there's a boatload of energy coming out of it versus a stupid hydrogen cloud that's trying all it can to give off one wavelength, okay? Most of what we see these stars, and you look back at these galaxies, you got a whole galaxy of stars giving off hydrogen lines in the optical part of the spectrum, and you say, my God, they aren't here. Then you look down in frequency and longer wavelengths, you say, wait a minute, what? There they are. Yeah, they're spaced just right, except they're all shifted down. And if I work it out, that thing is going away from us at this fast. The same way I did it here, except they do it with light. And the further back they go, the more redshifted they are. Which brings us to a current point. Why the heck do we spend so much money putting Webb up there? Who cares about the infrared spectrum? It's because when you go way, 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 way back, those visible lines are shifted down into the infrared, where they won't come through the atmosphere. So you put a telescope like Webb up there so that you can see the infrared spectrum, and you can find the hydrogen lines shifted down into the infrared. And this means you can see that much further back before you're towards the Big Bang. This is all called spectroscopy. This is radio spectroscopy. What you're seeing here, you gals all have radio spectrometers. If you've got a spectrum scope, either my Yaesu FTDX 101 has got a spectrum scope, if you've got this sort of a display somewhere on your radio or something, well, you're doing radio spectroscopy. We're just doing it a little bit more accurately and, you know, using a little bit different. Okay. Other questions? That's great. Yeah, I got to talk about Webb. Okay. Webb is 1 million miles away. And one of the problems with Webb is that the Earth is giving off infrared radiation. And one of the I was going to set the telescope up here and operate it, but the weather was lousy. And I also figured out, you know what, we're going to have all kinds of noise here. It's going to cover it up. Webb had to be put away from the Earth to get it away from the Earth so that the Earth is, very small, I mean, and the other thing was that it has this special shield that they have on it. That was one of the big headaches. To prevent the infrared radiation from the sun. Obviously, the sun is putting out a lot of infrared radiation, okay? And so they had to come up with this shield that would prevent the thing from being affected by it. It's just an amazing piece of equipment. I wouldn't want to be the person on that team that set the command for it to unfold and then go, oh God, did it unfold? Thank God. Well, we lost a couple of Mars spacecrafts that did not, I won't rag on NASA, but it has to do with the usual getting rid of the older people and so forth. They gave the signal for one of the Mars orbiters to go into orbit and it crashed into the planet. And you know what the problem was? The thrust on the engine was specified in pounds instead of in newtons. Now there's 4.5 newtons per pound. So one way or the other, it was overpowered by a factor of 5 or underpowered by a factor of 5. But just think about when it didn't do what it was supposed to several minutes after they gave the command because of the light travel time. And then someone sitting there that day or the day afterwards, looking at the specifications for the motor, and they look at it and they go, oh my God. Oh my God. Oh no. I mean, this has happened. Any other questions? Yes, sir.
Several years ago, that guy down in Ohio, Bob Dixon.
Yes.
Okay, is he doing the same kind of work?
He was probably doing radio astronomy. Ohio State, well, I can be careful. Ohio State University has an old radio telescope there that was a transit telescope. It was designed, it's called Big Ear. I don't know if it's, I don't think they use it anymore, and I don't even know if it's physically there anymore. A radio telescope does not have to be a parabolic dish. You can make a radio telescope with Yagis and stuff like that if you want. In fact, one of the things, Jupiter actually puts out a signal at about 20 megahertz. You have to know when to listen for it and so forth, but all you can do is listen to it. You can't really, do anything in it. And there are also that if you're really seriously into it, some of the older radio telescopes are available for use if you put in an application for, you don't go there and use it. It's computer controlled and you just get the data and you can analyze it and so forth. But to me, it's more fun to have my own, and I think the whole system costs less than $400, not including the computer, not including the laptop. So other questions? Yeah.
So, on your first slide there, you said, yeah, it's your kind of filters out.
Yes. Oh, yeah.
Violet, infrared.
Yep.
There was, I don't know what it was I saw on TV, but somebody said, who got hit by a cannon first? We got toast.
No, because we are already, hold on. Why are we, for instance, so concerned about the ozone layer? Anybody know? It protects us from ultraviolet. Ultraviolet is up here. And ultraviolet can be damaging and cause cancer. Ultraviolet causes sunburn. And so we obviously get some sunburn, or we get some ultraviolet penetrating the atmosphere. But if the ozone layer is affected, it could be much worse. And studies of it showed that certain fluorocarbons from spray cans were migrating up to the upper atmosphere and reacting up there and taking out the ozone. And Freon The first type of freon was a problem. So we stopped using it, and now it's restructured itself. Earth is a very special place because some of it's got to come through, but not too much. And too much the ultraviolet that we are typically exposed to is the long ultraviolet. It's just outside the visible spectrum. If you go back to, these things don't have definite breakpoints. Oh, it was the second slide.
Like the old black lights that make.
Black lights are ultraviolet. There's near ultraviolet and there's far, just like there's infrared and thermal infrared and so forth. The breakpoints between these various regions are not like this is in and this is out. It's a very gradual sort of thing. Let me, how do you even know? How do we even know that the infrared and the ultraviolet are there? Did anybody know how we figured that out? Well, people would run sunlight through a prism. Everybody knows a prism produces a rainbow. And so early experimenters, Newton and his people right after that would take a prism, take the sunlight, run it against the wall and produce the spectrum on the wall. They found out that if they stuck a thermometer down here below the red, that the thermometer would go up. And if you block the sunlight where there was no light there, the thermometer would go back down. And this is how they discovered that there was light below red or infrared, and like same thing with ultraviolet. Okay, and Spencer's stores specialize in fluorescence. Fluorescence, we don't know, is the process where you take ultraviolet light and it hits a chemical, and the chemical converts it to visible light. So if you've got or a mercury vapor lamp produces a boatload of ultraviolet light, but then it has a substance in there that will convert it to visible light. And it turns out that's more efficient than heating up a wire like an incandescent bulb. So there's no hard line between all of them, but down in this area, got to hit the right one here. I'll go back up all the way. We want to go down one page down. There it is. That web is down here in the this infrared down here, and up here there's a gamma ray. There are gamma ray telescopes, and there are X-ray telescopes, and there are some ultraviolet telescopes and so forth. I forget COBE. Cosmic Background Explorer is in the microwave region. And let me talk about that. There were a couple of guys working for Bell Laboratories, a little history of radio astronomy, that Carl Jansky was working. Bell Laboratories is big name in all this, okay? Carl Jansky was working for Bell Laboratories, and this occurred right before and after the war. It was in 1933. He was trying to get noise out of their communication systems, and he was working at HF, our frequencies. And they said, if you get rid of this noise, we can improve the communications, right? Well, what he found out was that he was able to identify several different sources of noise. And one of them he identified was lightning crashes. And he figured out there were far lightning crashes from all over the world. This is why we love 80 meters and 160 meters in the spring and the winter, or okay. He discovered those, and he discovered far and close lightning flashes, lightning signatures. Then he found this other one, this third one, and he couldn't figure it out. First, he thought it was, who asked about the sun? He thought it was coming from the sun. And it turns out, I'll try that. I'm pretty sure I can detect the solar noise from the sun, okay? He thought it was from the sun, but he eventually figured out it wasn't. And what he built was, you can go online and see it. It's essentially a bunch of dipoles at around 21 meters or something like that, okay? And you can see this, made this big wooden structure that he put on a big, he made a circular track of, and you can see it, I think, down at Greenbank, of cinder blocks. And then he used model Ford wheels, and he had this big long thing, 100 feet long, I don't know, that he could turn, and it essentially carried a bunch of dipoles. Okay, and he could turn this and run it into a meter and get the hiss and measure the strength. And he eventually could not figure out what was going on. And so he went to an astronomer friend. He thought that the noise, this unknown noise, came and went with the sun. So what would you think? If it rises when the sun comes and it goes away when the sun goes away, it's the sun. But then when he looked longer, he discovered as the weeks went on, wasn't synchronized with the sun. Didn't rise and set with the sun. Just like my particular point in the galaxy I've been looking at, doesn't rise and set with the sun. It shifts a couple hours every month. And he found that his radio source shifted a couple hours every month. The conclusion was it was coming from outer space. And back at this time, because they knew about skip and everything like we all use, right? They said no radio waves are going to come in from outer space because we can't get them out. Why are they going to come in? But he showed that in this case, this thing was coming from someplace extraterrestrial. And in 1933, he gave a paper. And unfortunately, he gave it to an electrical engineering group. And they're going, yeah, you know. But then when he talked to the astronomers, there was a guy named Reber who got really interested in it. And Bell took him off the project. You know, he said, you know, okay, maybe it's out there, but we don't care. We can't control it, so go work on something else. So he couldn't continue. Reber built a big dish and was able to verify that not only was it extraterrestrial, but was coming from the center of the galaxy. Okay, let me finish with one thing. I'll finish with one thing. When you look at those big telescopes, let's see, your camera's right there in the middle, right? Yep. Okay, so let me bring this on. Let me know if this is this in the view of the camera? Okay. Can you see it okay? Can you see it okay? Huh? Okay, all right. One thing you might have a question about is the holes in it. Okay, all right. By the way, what do you think's up here? Yeah, there's a dipole. There's a dipole in there. This thing reflects all the stuff up to the dipole. This part here, some of it comes up directly, and some of it comes. This stuff comes up like this and is bent back down into there. Okay. But as long as the rule is this for parabolic reflectors, as long as the imperfections are smaller than about 1/10 of a wavelength, that's the general rule. So that the waves arrive within 1/10 of a wavelength of each other, they're going to arise in phase. As long as the imperfections are less than 1/10 of a wavelength, it'll work fine. This is the same reason in a microwave oven you can have holes in the front. The holes are much smaller than the microwave ovens, by the way, operate at 2,450 megahertz. That's one of the allowed frequencies for them. This is at 1,420. Okay. So if the wavelength is 21 centimeters, 1/10 of that is about 2 centimeters. Well, you know what? All these holes here, these gaps, are less than 2 centimeters. So that's fine. Okay. Also, this is polarized. This is polarized. No one has asked, what is this a full 1 meter dish? Is it a full 1 meters? No, it's narrow. What the hell's that about? Well, you know, I thought about this. This is a dipole. Do dipoles pick up off the end? No. This dipole this way is not going to, you know, it's like this. It's not going to pick up off the end. So why put anything to reflect signal to it? All it does is add to weight and cost. But this way it picks up fully. So they can shorten it this way make it this way. And by the way, the surface has to be accurate within 1/10 of a wavelength too. Okay, all right. So on Webb Space Telescope, that's a parabolic reflector. It's it's got hexagonal segments, but it's still a big parabola. The wavelength is maybe 10 millionths of a meter. And so a millionth of a meter is 1,000th of a millimeter. You know, look at a ruler. That the surface of that mirror has to be accurate over its entire surface within 1,000th of a millimeter. And if you go to that antenna at Green Bank, that big huge one, the upper frequency limit is determined by the accuracy of the surface. If they want to operate at a wavelength, I think that might go to the millimeter range. It actually might go down to the millimeter range. So the surface of those, how big is that telescope, do they say? And it's like, imagine a 25 meter telescope, 75 feet across. 75 feet across. And over that entire surface, it can't be more than a millimeter or a 20th of an inch off anywhere throughout that entire surface. It's not just, it blows.
You have to deliver it to space without damaging it.
Yes. Yes. And it has to survive wind loads. And then you have to be able to steer it. You know, this one will be steerable. I can steer this one. But that's another story. You know, I can point it down. And of course, there's always a side. What happens when I point it down? Say it. Noise. All those wonderful things when all the noise is behind it. Great. If I want to point up there, well, now all the stuff that's propagating coming in, that's going to be a problem too.
Is the hydrogen line you've been talking about, does it have any polarization to it?
No.
Randomly?
No, it's not. Now I'm going into moon mounts too. Anybody here? Now I'll talk about moon mounts when I do it. I just built a 1.2 kilowatt 2 meter amplifier. Okay, the power supply is 50 volts at 50 amps. It's a mother. Okay, it's solid state. And I have a transverter that I'm going to be using with it, and I'm going to use FT8 or whatever. I got to talk to you, Anthony, about FT8, but I don't want to use FT8. I want to be able to go dit. And 2.5 seconds later, hear my radio go dit. And then after I get that, I'll go from there. But these antennas have to be unbelievably accurate. And of course, they age and they're subject to wind and snow and ice and all that. Anyway, thanks. We've been here a good time. And I knew people would be fascinated. Thanks for having me. Come and take a look at it. Yeah, it's pretty cool. You know, some people have said they already got the antenna. So put it to use, you know.
Great job, Craig.
Thank you
Very much.
Who's talking to me here? I can't.
This is Pat.
He's on Zoom.
Oh, you're on Zoom. Okay, thanks, Pat.
Yeah.
Isn't that amazing?
No, I'm not. I'm gonna flip it.
I'm gonna move this out of your way.
That's good.
Hold on, this will fall off. Yeah. Yeah, Greg, let me move this.
Yeah.
Hey, Anthony, did we get a head count?
Don't leave. We still have a little bit.
Yeah, we still have a couple things going on, so everyone do not leave. We do have a head count. We'll give that to you in a moment here.
Thank you.
They came in late.
We have one.
Sign the attention sheet.
We have one more to add to it. W8HFY just is on Zoom.
Attention sheet.
HFY, Dave Wright.
It's really nice. Yes.
You want it?
Yes. Yes, yes.
25.
Stand right here. Right there.
I just wanted to mention the next meeting
which is normally scheduled as a business meeting. We're gonna minimize, we're gonna minimize the business part. And Frank's gonna continue his discussion concerning our repeater. And it's an interactive discussion. So think about the things that he talked about last time, and what you'd like to see with our club repeater. Because we want everybody's input so that what we do pleases the majority of the club. We're gonna give you that. And then the next meeting in March will be Anthony with 10 meters for everyone. I saw him give that presentation, so I know you enjoyed that as well. A couple little things here. We've got a door prize and the random number 9. Well, believe it or not, Pat won it, and I will get the prize to him.
What is it?
ARRL mug, get that to him. And the last thing, I have some Radcom magazines up here that I've read. And rather than throw them out, I know most of you probably don't subscribe to that, so I brought them here after the meeting if you want to come up and help yourselves to those magazines.
I have one other announcement. One other shameless promotion. Last Christmas, I mentioned I was putting out a record. I've done it. And if anybody's interested in the CD, I bought something. The DJs like it, but you know, anyway. And somebody wanted business.
Okay. Yeah. Maybe you can shut them down.
Okay, well. Any other announcements? Any other questions from anyone on Zoom?
Again, the next business meeting, we will be discussing repeater improvements. So bring your ideas.
Okay, we're gonna go ahead and end the Zoom session. Thanks, everyone.
All right, thanks, guys.
7-3.